Assalamualaikum and good evening. Now we are going to discuss about vibration analysis and monitoring in our lecture 8. Okay, now this time we are going to discuss about shaft condition monitoring. First, we will focus on what is condition monitoring is all about. Okay, same like gear condition monitoring. In general, condition monitoring aims at detecting faults to minimize production costs and optimize predictive maintenance. Maknanya sama macam ketika kita membincangkan tentang tajuk gear condition monitoring, shaft condition monitoring sama matlamatnya untuk kita mengenal pasti kerosakan agar dapat meminimize ataupun meminimalkan kos pengeluaran ataupun kos operasi dan juga mengoptimiskan ramalan penyelenggaraan ataupun optimize the predictive maintenance. Dan sebenarnya condition monitoring ni ataupun pemantauan keadaan ini adalah satu kaedah yang terkedepan di dalam teknik maintenance rawalan. So untuk sebab itu pengesanan awal, pengenalpastian dan juga pembaikan masalah-masalah pada peralatan mesin adalah amat penting dan ini terutamanya yang bagi mereka yang terlibat dalam industri pemesanan yang fokus kepada penyelenggaraan untuk memastikan operasi yang selamat, yang dapat berterusan dan produktif. Dalam hal ini, shaft merupakan satu komponen penting dalam mesin yang berputar dan kegagalan di dalam komponen shaft ini akan menyebabkan malapetaka di dalam industri yang terlibat. Boleh dikatakan selain daripada gear, shaft juga adalah penting. Dalam rotating shaft ataupun shaft yang berputar ini, kita boleh dapat kenal pasti getaran yang dihasilkan dan kebiasaannya shaft bergetar disebabkan oleh unbalance, ketidakseimbangan, misalignment, ketidaksejajaran dan juga kerosakan pada shaft. Jadi gangguan yang berlaku dalam shaft ni akan dapat dikesan menggunakan pengesan yang bersesuaian dan biasanya pengesan tersebut kita gunakan accelerometer lah. Dan accelerometer ni tugas dia akan mengesan getaran dan data tersebut akan dihantar ke FFT analyzer, fast Fourier transform analyzer, yang akan menukar data yang dikesan itu di dalam komputer, yang mana kita boleh dapat elemen ataupun dapat mengenal pasti elemen frekuensi, amplitude, displacement, disebabkan oleh ketidaksejajaran, misalignment, dan disebabkan oleh itu kita boleh buat satu perbandingan dan hasil daripada data yang diperolehi itu, jadi maintenance awal ataupun penyelenggaraan awal dapat dilaksanakan. Seperti yang kita maklum, pemantauan getaran ini adalah satu kaedah yang sudah establish, dan dalam hal mengenal pasti keadaan syaf ni, kita boleh fokus ataupun pemantauan getaran ini dapat mengenal pasti apa yang berlaku ke atas syaf jika berlakunya imbalance ataupun misalignment. Dan kaedah yang ketara, teknologi yang ketara yang digunakan untuk mengenal pasti keadaan syaf adalah menggunakan kaedah analisis getaran. Dan faedah yang besar yang dapat diperolehi daripada analisis getaran ini adalah proses mekanikal yang berbeza di antara operasi mesin tersebut akan menghasilkan frekuensi yang berbeza. Jadi frekuensi yang berbeza ini akan diasingkan antara satu dengan lain menggunakan analyzer. So, untuk komponen syaf ni, dia terlibat dalam operasi yang performan tinggi, seperti apabila kita ataupun melibatkan kompresor, steam, gas turbine, generator, pump dan engine. Okey, kesemua komponen ini kebiasaannya banyak digunakan dalam proses dan juga utility ataupun di dalam bidang berkaitan proses dan juga utility. Contoh, kalau proses ni macam di tempat pemprosesan minyak, gas, utility ni mungkin terlibat dalam jana kuasa, penghasilan jana kuasa elektrik dan sebagainya. Jadi syaf ni adalah komponen yang amat penting dan dia melibatkan operasi yang berprestasi tinggi dan juga menghasilkan apabila dia melibatkan operasi yang berprestasi tinggi, bermakna ia juga melibatkan risiko yang amat besar jikalau berlaku kerosakan terhadap syaf ini, yang mana mungkin boleh menyebabkan pelan yang berkaitan dengan penyalaan tenaga ke atau pemprosesan bahan kimia akan kalau keadaan syaf itu tak dapat diselenggara dengan baik, jadi akan melibatkan satu malapetaka yang besar bukan sahaja terhadap industri, tetapi mungkin melibatkan sehingga ke makmuran negara akan terganggu. Dalam melihat ataupun memantau keadaan syaf ni, biasanya dia akan melibatkan 3 keadaan kerosakan syaf, iaitu imbalance, misalignment ataupun broken. Mesin yang melibatkan putaran ini, dia didesain ataupun direka untuk dia dapat beroperasi pada keberkesanan mekanikal yang tinggi, higher mechanical efficiency. Okey, jadi untuk mendapatkan operasi yang optimum, kerana syaf melibatkan pemindahan kuasa, beban dan juga stres. Disebabkan oleh itu, kebanyakan sistem dynamic rotor dia yang mengandungi syaf, dia akan terdedah kepada kegagalan fatigue failure, disebabkan oleh crack yang terhasil secara melintang. Fatigue failure due to transverse and cross-sectional cracks. So, untuk shaft fault diagnosis, jadi disebabkan oleh bias analysis ini adalah satu kaedah yang well established. Jadi dia akan menggunakan frekuensi spektrum yang diperolehi daripada pemantauan getaran ataupun daripada vibration monitoring untuk memahami respon ataupun tidak balas frekuensi setiap komponen yang terlibat. Yang mana jikalau tidak memahami secara menyeluruh hasil daripada data yang dipantau, hasil daripada vibration yang terhasil, jadi keputusan yang tepat sukar diperolehi. Apabila keputusan tepat sukar diperolehi, bermakna predictive maintenance yang akan dijalankan akan tidak menghasilkan keputusan yang dikehendaki. Seterusnya kita akan menonton video yang berkaitan dengan kegagalan pada shaft, utamanya apabila berlakunya imbalance dan juga misalignment.
Unbalance and misalignment create unique vibration spectra. With a fan, static, or force, unbalance appears on the spectrum as a higher than normal amplitude at 1x because extra force is being applied at each rotation. With couple and dynamic, 1x will also appear larger than normal because of force applied for each rotation. Phase relationships between bearings vary based on the type of force involved. Angular misalignment is categorized by high axial vibration with unusually high 1x and 2x and sometimes 3x in the axial direction. With parallel misalignment, there is high radial vibration and 2x is often larger than 1x. Amplitude can vary based on coupling type and construction.
Hello and welcome to this quick presentation on understanding unbalance. My name is Jason Tranter, the founder and managing director of Mobius Institute. Mobius Institute provides vibration training and accredited certification. So, unbalance exists when the mass centerline and the geometric centerline do not coincide. What does all that mean? So, the geometric centerline is the center of geometry, which for our fan should be right through the center of the shaft. So if we draw a circle around it and say, where does it intersect? Well, it should, if the machine's designed properly, go straight through the center of our shaft. And that's where it also wants to rotate. So there's our geometric centerline. Now, our mass center line should be in the same location. If all the mass is evenly distributed around our machine, then the center of mass would be right through the center of the rotor as well. But when that is not the case, when the geometric center and the mass center are not equal, then when we spin the rotor it will wobble, and that is unbalanced. Now I've got it offset to the right here, but of course it could be offset anywhere by any amount. So we need to reduce unbalance, because unbalancing increases the stress on the machine, which reduces the life of the machine and the structure. It will damage the structure. It can cause workers in the area to feel that high vibration. It can affect product quality. It can annoy neighbors. I mean, that's pretty extreme unbalance. But in any case, it can certainly damage the bearings and the seals. And if there is any resonance occurring, then the more unbalanced vibration we get, more amplification, and therefore much higher vibration. Same as if we have any looseness, then that unbalance drives the ability for it to be loose, if you know what I mean. If it's loose, then we get more motion if there's more unbalanced vibration. Okay, so the other key thing about unbalance is that the forces generated are proportional to the speed squared. So if we double the speed, we get 4 times the amount of force, or 4 times the amount of motion, which this little animation is attempting to show. So therefore, as we increase the speed, we will see higher vibration, which may not be something you intend to do, but what it really means is that for a high-speed machine, unbalance is extremely important. It is important to minimize it as much as possible. So, why do we get unbalance? Very commonly in fans, it's just a build-up of dirt. It might be a loss of material, through wear or cavitation or erosion or corrosion or something like that. It might be due to poor castings or incorrect roundness, for example, eccentricity. It might be a loss of a part. A balance weight might fall off. A fastener might come away. It might be loss of part of the coupling. It might be, in this case, just the way it's been put together, which is not sensible. Of course, this is a little bit obvious. But anyway, there's a lot of causes. We have to correct any mechanical problems that might exist, like missing blades and so on, but then we're going to go through the balance process. So, one way of illustrating unbalance, if we have a rotor here, and we put an unbalanced weight on, then in a single plane unbalanced case that we have here, the rotor will want to turn until that unbalanced mass is at the bottom, thanks to gravity. But if we let the rotor spin, then we're going to see a lot of vibration as a result. And of course, if we put even more weight, causing even more vibration, more unbalance, then we get a lot more vibration. So we need to minimize that unbalance that exists, and therefore reduce the unbalanced forces. So the most common type of unbalance with narrow rotors like the one shown here is called static unbalance. That's where all the unbalance is more or less in one single plane. We can see the characteristic motion of static unbalance. In this case, the center of mass is moved away from the center of geometry. So there's our center of geometry. As the mass, out of balance mass, is increased, I'm trying to illustrate here, the center of mass is pulled away from the center of geometry. Now, of course, when we run the machine, we mount it in bearings and design a machine to support it, but of course those bearings are now trying to contain those circular forces that we just saw a moment ago. In a classic case of couple unbalance, we have unbalanced mass that's 180 degrees opposite each other and equal mass. That's a very specific case of unbalance which you're unlikely to see in reality, but it's a term that you should understand. So in this case, as these two sources of unbalanced mass increase, it draws the center of mass away at each end of the rotor, but in actual fact, the center still coincides with the center of geometry. So we see the motion that we see there, but in actual fact, if we were to put this rotor on a knife edge, it wouldn't roll because statically it's balanced. It's just got a couple unbalanced. The more common situation that we would see with a longer rotor like this is what we call dynamic unbalance, where we can, consider the unbalance to be different masses at each end at a different angle, and it creates this wobble. And exactly how that mass is built up just depends on the root cause of the unbalanced problem. But when we look at how the center of mass is moved, we get a static portion and a coupled portion. So there's dynamic is there for a combination of static and couple unbalance. But of course, as with the other situations, our machine and structure has to withhold those centripetal forces, and that's what causes the damage. In the case of an overhung rotor, we get the radial vibration, the radial motion that we've seen so far, which I'm not really showing in this animation, but we also get a rocking motion, which you can see there. And so in addition to those radial forces, which cause damage, we also get axial forces. It's causing an actual force along the length of the machine, and that causes its own form of damage. So, in conclusion, unbalance is common, more common in some machines than others, and it is destructive to the machine. The forces associated with unbalance are far greater with higher speed rotors. Static unbalance is common in narrow rotors where the unbalanced forces are focused in a single plane. Couple unbalance is a special case where we have longer rotor, but the unbalance is equal and opposite. The same weight, but opposite each other at each end of the rotor. That's the way we can model the couple unbalance situation. But dynamic unbalance is the most common when we have longer rotors, and that's where, if we were to sum up all the unbalanced forces, they would not be equal at either end of the rotor and not exactly opposite each other. So, I hope this brief presentation Hello and welcome to this quick presentation on diagnosing misalignment. My name is Jason Tranter, the founder and managing director of Mobius Institute. Mobius Institute provides vibration training and accredited certification. First, we have to quickly understand what misalignment is. Shafts are misaligned when their rotational center lines are not collinear when the machines are operating under normal conditions. And a couple of the important points about that is, when a machine is cold and you do an alignment, it's possible that it'll go out of alignment when the machine is running, particularly if one or both components increases or greatly decreases in temperature. So we want the two shafts to be collinear, perfectly in line when they're rotating. Shaft alignment is extremely important. Bearings, seals, shafts and couplings will fail prematurely if shafts are not precision aligned. Unless we take special precautions, the shafts will not be collinear. There will be angular and offset misalignments, and that misalignment will exist in the vertical and horizontal direction. Think of it as a 3D issue, how it's exactly where the angles are and where the offset exists. So in this simulated animation, we've got the two shafts offset aligned, so we've aligned them but dramatically left them offset, and you can see the motion there. But of course, if we bolted the feet down, you can imagine the stresses on all those components. And if we have angular misalignment, we've closed that gap by attaching the couplings, and now we've put stress on all those components again. So what do we see? Now we can see high 1x vibration, and we can see high 2x vibration. It's very common in vibration charts and so on to just focus on 2x. you may see high 2x vibration. You may not. It's common to also see the 3x, 4x and 5x peak increase in amplitude, even to the extent where you may be thinking it's looseness, but looseness will generally have more harmonics, the noise floor might rise up, and the phase relationships are very different. And the other thing to consider is that in the case of misalignment, if we compare the vertical and horizontal phase, there will not be a 90-degree relationship between the two, as we would see with unbalance. So it's easy to confuse the two in certain circumstances, so that's one way to rule it out. We can also look at the phase difference on components either side of the coupling and see if we see either the 180 degrees opposite in the vertical direction or in the axial direction. So the key is, though, to make sure you're not just looking for that 2x vibration. And it's also important to note that we can have misalignment without the vibration changing in a characteristic way. Okay, so if there is angular or gap misalignment, then we expect to see far more axial vibration, particularly at 1x. That's because we've got this gap, and if you like, it's a push me, pull you situation, and we'll therefore see the phase out of phase when the phase readings are corrected in that axial direction. It's very important to understand, though, that the coupling type greatly affects the vibration that you will see. So whether it's a tire coupling, or any grid coupling, gear coupling, whichever type it is, a jaw coupling, they will generate vibration themselves potentially. And when there's any small amount of misalignment, that will exacerbate the vibration at certain frequencies. For example, a 3-jaw coupling might create vibration at 3x, but that doesn't mean that's all you will see in the case of misalignment. So misalignment is a rather complicated fault to diagnose. We can use time waveforms. We certainly should use phase, and the spectrum is very good. So offset or parallel misalignment will generate higher radial vibration. That's sort of the vertical and horizontal. The 2x peak may be elevated, as in it might go up in amplitude, but it is important to also look at the 1x, 3x, 4x and 5x peaks. Gap or angular misalignment will generate higher axial vibration at the running speed, 1x. Misalignment may exist even if it is not evident in the spectrum. So just because you're not seeing a lot of the symptoms of misalignment in your spectrum, that does not mean that the machines are precision aligned and therefore that the bearings will fail more quickly than otherwise. And we should use phase to confirm that misalignment exists. Well, this is a quick introduction.
Sekian, terima kasih.